of neural network compression. All right, no surprise there. Who's here? Who here's heard of image compression? Compression of images. Yes. Very important and helpful in a lot of ways. PNG, JPEG, all of those are compressed image formats. And turns out you could do a similar thing for neural networks. You can make them smaller while maintaining similar accuracy and performance. So let's get straight into it. So, neural networks are very, very big. I don't know if you guys have played around with models yourselves, but they can become huge. A lot of the ones that we'll see for our daily tasks won't be that big. However, when you start to get into the realm of like image classification, for instance, this is VGGNet, which is a image classification, which is based on the data set ImageNet. So ImageNet is a data set, VGGNet is the model. And it takes in a 224 by 224 image, RGB, and is able to identify what object is in that image. And there's 1,000 different labels. They could be a car, a dog, a deer, all these types of things. And this requires a very large model. I think this one in particular has around 150 million weights that need to be changed. So 150 million weights, that's a lot of weights that you have to store, do calculations on. And it only starts to get larger from here. Let's look at more modern models such as GPT. Everyone here, as I'm sure, have played with ChatGPT to some extent. Here are some of the examples of ChatGPT 3. So if you look at the small ones, again, small being not too big, only 125 million parameters. And you look at the full-size GPT-3 model, it's 175 billion parameters. And again, this is GPT-3 we're talking about, not even the newest ones, GPT-4, whatever Google's making now, Llama 3, those get even larger. Because of the size of these, there's a lot of different problems you can have. Again, just a large size and inference time. So why is having smaller networks important? They're important for a plenitude of reasons. Who here has seen this YouTube video before? It's hit big on the YouTube algorithm last week. For those that don't know, this is a review of the Humane AI pin, which is essentially a AI assistant that you could put on your shirt right here, and it's supposed to you're supposed to be able to talk to it like you do with Siri or Google. But the thing is, it's so small, there's no way it can compute all of that. There's no way it can listen, calculate what to respond with. So everything that it does happens in a data center. Anytime you want to ask it, how tall is a Seattle Space Needle? It'll go to, let's say, Google's data centers. It'll then run the simulations, and then it'll have to be brought all the way back over the internet to this device. And that was one of the biggest issues with this, is it just took forever. You would ask it something and it would take 10 seconds to respond back. It was a huge problem. And partially this is because modern models are just gigantic. Not only do they take up so much space, as seen by the millions or billions of parameters of these models, but they also take a lot of compute power to actually make inferences or use them properly. So again, here's a quick summary of what we just mentioned. So one, the parameters that are the model weights, so things that we use to calculate and multiply across. These are stored in matrices or arrays. And again, they could take up a lot of storage space. We're talking billions of parameters. And each parameter being a float. Again, this should just get larger and larger and larger. And is something we probably want to think about. Additionally, the larger these models are, the more numbers we have to multiply, the more computationally expensive it is. For instance, if you were just running a simple model, you might be able to do it on your phone. Your phone has limited amount of computational power, can only do so many matrix multiplications so much. And the larger it is, the more multiplication or matrix models we have, the matrix computations we have to do, and the longer it takes, and also the amount of memory we'll need to load the model. And so the big issue is when it comes to edge devices, such as the Humane AI pin I mentioned earlier, and your phones. These are all edge devices, things you wouldn't see in a data center that you might carry around with you every single day. And again, the more computationally expensive something is, more energy it's going to require to calculate these types of things. So you wouldn't want to be um, running a machine learning model on your phone, as it might just completely waste your battery power. Go through it really quick. Also, another issue with the humane AI, just drain through its battery. So I guess a question for you guys: what are some examples of why we'd want to run machine learning models locally on these edge devices? What's wrong with just keeping them on the data center? So what kind of examples you feel like would be important to be able to run machine learning models on a device? I don't have any ideas. So yeah. Mhm, mhm. Absolutely. Yeah. Mhm. Yeah, absolutely. Anyone else have any other ideas? Yeah. Mhm. Yeah. Yeah, all these are really good examples. Does anyone here have a Pixel device or Android? I don't know if this also exists on iPhones, but they have a built-in closed captioning that happens locally on the device. So it takes the audio as an input and is able to translate that um, into a caption for you, local on devices, where oftentimes this will have to be sent to the internet to then be transcribed back down onto your phones. It's a lot of different examples of these. Here are some that might be important to have done locally. I think we mentioned what happens if you don't have internet, such as CCTV or motion tracking, right? What if you have a cabin in the woods? You still need some sort of models to be run to identify, okay, was this a bird or was this actually a human person that came and intruded on my house? Additionally, a big thing is privacy, such as in hospitals where you can't just throw around patient data. HIPAA violations are very important. You got to make sure that your medical information is private. And so these types of things might not be able to be stored or sent to OpenAI's servers. You need to do everything locally. And this is another key part where you want to make sure your information stays within a place that you can control. You can't just be sending it around to Google's data centers or send it to Microsoft. Another one that no one's had mentioned is self-driving cars. It's something that needs to happen on the fly. It can't just always rely on internet. Because if all of a sudden your driving cell tower goes out, what is it going to do? It can't just crash into the car in front of it. You need to have all these calculations done locally on the fly as well. Luckily, self-driving car computers are a little bit bigger than what you have in your pocket, so they should be capable, have a lot more capability when it comes to performing these mathematical computations. So today we'll be going over three main types of model compressions. We'll be mostly looking at neural networks. So all these will have to do with changing the connections or different weights of these. The first and main one that we'll be looking at is called neural network pruning, which essentially looks at the different connections or weights parameters of these models and decides which of ones of these are not important. And we'll go ahead and remove. Quantization has to do with reducing the precision of these weights. So a lot of these weights are stored as float values. And as we know, floats are made up of bits. I think the most typical one is float 32. That's 32 bits. Well, if we can change it to int 8 without reducing accuracy, that would be a good way of reducing the total size of the network, just decreasing how large each of these weight values is. Finally, knowledge distillation, which uses a teacher model and a child model. It uses a teacher model's information to train a smaller child model. Again, we'll go through all of these later throughout the presentation. So we'll start off with neural network pruning. As I just mentioned, pruning just removes unneeded components of a network. And sometimes they can be individual weights or connections, but they can be even larger, such as full layers, neurons, CNN filters, and more. It just has to do with what is not needed when it comes to maintaining accuracy with these models. And when I say pruning or removing a node neuron from a model, this typically means zeroing out their weight values. So for instance, if you have a weight that is value of 1.2, If you were to prune it out, instead of just removing it entirely, we just set it to 0, as when we go through all the matrix calculations, it is no longer included because 0 times anything is kind of 0 and nullifies itself out. So can anyone tell me what might be a good way to identify whether a neuron or connection is good to prune? Might not be important in the calculations of the neural net. Yeah. Yeah, that's pretty much the bog standard way of figure out pruning methods. If it's close to 0, it probably isn't that important if we change it to 0. Is there another question? Any other methods anyone has? Well, we got the main one right here. It's called magnitude pruning. Technically, you can also do random pruning, and it's surprisingly decent. Obviously, it's not going to be the best, but it's another way. So that is another cool thing. So I'll do a quick recap of how we calculate a neuron's value using weights and inputs. So as you see on the far left, we have our inputs, 5, 3, and 4, and we have all their weights. This is an example of a very simple linear layer. These weights are those parameters that we talked about that we would want to be pruning out. So we take each input, multiply it by its respective weight, sum them together, including a bias, which is just like think of it as in y equals mx plus b. This is the b in that very simple linear equation. Some bias that we had here. Throw it through an activation function. This could be a linear function, which is just y equals x. Could be sigmoid, ReLU. Not going to go too into depth into all those, as we've talked about those in a previous session. But once we combine all those together, we're able to get our output. So again, 5 times 0.2 is 1. Add that to 3 times 2, that's 6. So that's 7. Then do 4 times 0.753. I don't know why I'm doing this on the fly. 10 minus 8 is 2. So that's how we would get the value of the neuron. And we'd multiply all of the inputs and weights, sum together, incorporate the bias, go to the activation function, get our output too. So what should we prune? As we mentioned already, we would want to prune the smallest weight. But what if we did the opposite and said we pruned the times 2? How would that actually affect our output? So if we change it to times 2, our output would become negative 4 from 2, as we know because of this used to be a times 2, so 3 times 2 would have been 6, so we're actually reducing our neuron value by 6, which is a significant difference. It would make a huge impact on our model's effectiveness because we're just removing a very impactful piece of information. However, if instead we removed the 0.2, it wouldn't make too much of a difference. Our output went from 2 to 1 because decreasing 0.2 all the way down to 0, again, isn't that big of a change. And so that's why we come up with our magnitude pruning method. This takes the absolute value, so it's able to equally look at both negative and positive weight values. And a similar thing works with a lot of different other pruning methods where it has some sort of identification of what defines an important node or important weight value, and is able to remove the lowest k% or some ratio of those nodes. And again, we're simply removing the smallest absolute value of the weights. How do people feel about the concept of magnitude pruning or removing the smallest absolute value of weights? Okay, some thumbs up, thumbs middle, thumbs down. Very cool. Great, glad to have everyone following so far. So there's a lot of different add-ons to pruning. We just talked about the most basic concepts. Well, there are a lot of different things you can play around with. First, we'll talk about local versus global pruning. So local pruning is where we're only comparing weights based on each layer. So if we look at the diagram over here, on the left, this is local pruning. So we say, hey, I want to prune 50% of the weights on the first layer, and we'll do that. And then you do in the next layer, okay, I want to remove 50% of those, do that, and so on. You do 50% of every single layer, or you could choose whichever percent you want. However, this is a per layer calculation. So just because one layer has all the biggest ones, it doesn't really affect all the other layers. On the other hand, global pruning prunes weights relative to the entire network. This means if you have one layer that is consistently smaller than the rest of the network, you might have them 80% of the second layer pruned out, but maybe the first layer has a lot of large weights. And so you'll have only 20% of that layer. And so these are the two main different ones, local and global pruning. They both work pretty well. One thing that you might want to keep in mind is if you're going to do local pruning, you're going to want to identify what pruning rates you want for every single layer. Because if you just set every layer 50%, you won't get as good of a result as compared to if you, let's say, knew somehow that pruning 30% of the first layer, 60% of the second layer, and so on was better. So local pruning, global pruning work pretty well. Just keep in mind if you're going to do local pruning, try to have different percentage pruning ratios for each layer. Sparsity problem is probably one of the biggest issues when it comes to pruning and why pruning isn't necessarily the go-to solution for model compression. As we mentioned, pruning removes weights by just zeroing them out. And when you use what's called unstructured pruning, we're just kind of zeroing out almost seemingly random weights. Yes, we talked about how it's the magnitude is important, but we end up with the sparse matrix that looks something like this, where the sparsity is defined by the number of zeros in it. And while yes, this matrix is a lot simpler, because there's a lot of zeros and a lot of non-zero values, it's still hard to do matrix multiplication computations with sparse matrix. It doesn't actually increase or decrease the computational expense of these different calculations. So, well, yes, it can reduce the size of the network because you are zeroing out a bunch of things. Oftentimes, it won't actually make your inference speeds any faster. On the other hand, there's this concept called structured pruning. So what we just talked about was unstructured, where we're just removing weights independently of one another. Structured pruning is where we remove entire components of the network. So before we just talked about removing weights. Well, structured pruning says, hey, if we remove entire layers, entire neurons, entire CNN kernels, that will do a lot more for our speed. So the actual time it takes to predict whether something's a cat or dog will be faster if we can remove an entire layer outright. So while yes, you don't end up with as sparse matrix, it might also see a more reduction in accuracy by doing a structured pruning. So it's kind of a trade-off of those. For unstructured pruning, you get a lot smaller network simply because there's a lot more zeros. However, with structured pruning, you can actually get a faster inference time simply because you're removing entire components. Technically, in order to take the most out of all these, you need to have specialized hardware. Oftentimes, you might prune a model, and just because there's a lot of zeros, it still is very slow. And same thing with structured pruning. But there's some hardware, I don't quite know specifically what hardware it is, but you can do sparse matrix math really efficient. For your typical GPUs, you can't really do that with. So, yeah, question? Mm-hmm. Yeah, so you're right. It should technically still be unstructured pruning should technically still be a faster improvement off of the original method, but it's still not that significant. Right. So it's like saying multiplying a 5 by 5 by another 5 by 5 matrix, no matter if there's zeros or not, it will still take a decent amount of time. There's some zeros in there, it'll be faster. However, if you multiplied a 5 by 5 matrix by a 2 by 2 matrix, regardless of if there's zeros in it, it will be significantly faster. Just from how computers are able to calculate matrix multiplications. Again, specialized hardware is able to do sparse matrix multiplication really efficiently, but we don't really have access to that kind of hardware. Okay, yes, yeah, you're right. So if we just remove nodes that we say are not very important, no surprise, but our models perform worse, right? If you just start zeroing out weights that our model is trained to, our model won't be able to predict it very accurately. That's kind of seems intuitive, right? And we can recover this accuracy or performance through fine tuning. Has everyone heard of fine tuning before? Is there anyone who hasn't heard of fine tuning? So fine tuning is essentially taking a model that already works, whether or not it works well or not, and using those existing weight values and continuously training with that as kind of a starting point. So instead of starting off with when all the weights are 0 or randomized, you're starting off with when the weights have hit a good checkpoint or a good level. And this is what we'll be doing with pruning algorithms. You prune them, the weights that we haven't touched or haven't zeroed out still can maintain weights or values that they did from the get-go. And so what we'll do, we'll take those that used to perform really well and we'll slightly change them through fine tuning. So maybe originally we'll use a learning rate of 1/100th. Now with fine tuning, since the weights are already pretty good, we only want to change them a little. So we might use a learning rate of 1/10,000th or something like that. That's much smaller. So all we're really doing is kind of nudging our weight values in the right direction. We're no longer retraining from scratch. And doing so gets results a lot better than pruning a network and then training from scratch. So after you've pruned, make sure that you are fine-tuning or continuing to train the model to recover some of that accuracy. And interestingly enough, sometimes after pruning a network, you can actually get higher accuracy than when you started out with. Just a fun thing. If anyone's interested, there's a big paper called the lottery ticket hypothesis that claims only a very small portion of the neural network is actually necessary. A couple things to note about pruning and retraining is the concept of one-shot and iterative pruning, where one-shot pruning is where you prune a model, you retrain it, and you're done. It's pretty straightforward, and that might get you a pretty decent result. However, it's been learned that iterative pruning is significantly better. So let's say your goal is to prune 90% of your model. One-shot pruning would be you prune all 90 at once, retrain, and you're done. Iterative pruning says if we prune and fine tune multiple times, maybe at smaller steps, our result will be significantly better. So if our goal is 90% sparsity, we'll prune 30% at a time, we'll fine tune it, do another 30%, fine tune it again, do another 30%, and fine tune it until we finally have that 90% sparsity. So when you're pruning your neural networks, I highly suggest iterative pruning, where you prune, fine tune, and repeat instead of just doing it one big chunk at a time. Does anyone have any questions about pruning? Here's a little summary of what we talked about. Again, I don't expect you to memorize all of those words I said. Just kind of get the idea of, hey, pruning is where we remove non-essential pieces of the network to be able to have a reduced size model, hopefully also get a faster or less computationally expensive inference time as well. All right, cool. Let's move on. Does anyone remember what the definition of network quantization was from the slide, probably like 10 slides back? Yeah. Exactly. We are reducing the precision of each of the weights. So here's a quick review again about how do computers actually use numbers. If you've taken, CSC, gosh, 12 or 120, you've probably seen all this a lot. As well know, computers can only read ones and zeros. There's no concept of being able to just see an image and understand it immediately, unless we're talking about quantum computers, which we're not. And that also means that it's not possible to just store infinite precision. We can't just define irrational numbers with perfect precision or accuracy. And we can only store things with ones and zeros. So for instance, with a 64-bit float, we can only define 1.8 times 10 to the 19. I say only, that's a significant amount of values that we can store right here. But again, the more we limited by the number of bits to store a number, and number of bits also determines how much large storage a single number takes up. So for instance, if we looked at 64-bit floats and we tried to store every single one of GPT-3 weights, that alone would be 1.4 terabytes of data, just the weights alone using float 64. Thankfully, we don't actually use float 64. The main method is float 32, but we get the idea where storing these models can take up extraordinary amounts of space in our systems. And if you want to run this at home, there's no way you're going to be able to free up 1.4 terabytes, or I think half of that would be 700 gigabytes of space just to hold the weight of GPT-3, not including being able to actually calculate and multiply it out. It is significant, and we haven't even got into memory as well, storing all this stuff in a GPU as well. So quantization helps you reduce this amount of storage by decreasing the precision of these weights. So float 32, which holds 32 bits, can be then converted into values such as int 8. So we're converting floats to integers that only contain 8 bits of data. And this will save up to 4 times the storage space because we're converting again from 32 to 8 bits. And this might seem quite confusing because how do we represent a float as an integer, especially if we're talking 0.3? How do we represent as an integer? You can't store 0.3 anyway at all. And we won't quite get into that, but you would have to be able to map everything to integers, convert everything, and so that the end result gets you to your ones and zeros at the end. Again, I'm not going to go too into depth into that, but one of the nice things about converting it to integers is doing integer mathematics is significantly faster. I'm sure most of you guys can do 16 times 3 faster than you can do 16.398 times 14.77, right? Integer math is significantly faster than float. So not only are we saving storage space, we're also being able to compute these models significantly faster, and also have a lower memory bandwidth, or how much memory we actually need to store on them. Obviously, this will come with a cost of accuracy, depending on the model and how you have quantized it as well. An interesting thing for quantization is you can do this both after training. So this is like a static. So you've taken your typical model, you've trained it the normal way. You have all these weight values are all floats. You can then convert all of that into integers via quantization. That is one way. Or you could do quantization while you are training. So you're training your model specifically with the knowledge that you will quantize it later. I don't know exactly how that new training works, but it happens during training, or you can just take a regular model and quantize it after the fact. The next compression method is knowledge distillation. This is a concept which uses a teacher model, or the original model that we have, and using it to teach or transfer knowledge to a child model, or a model that is smaller. And typically you would want the child model to have a similar architecture as the original one. You could do this by taking the original one and removing a layer yourself, changing how large each layer is. But typically you'd want to keep the structure or architecture of this child model to be somewhat similar. And the idea behind knowledge distillation is that the teacher model works relatively well because it knows some knowledge that is stored in the weights. And the goal is to be able to take that knowledge, distill it in some form, and transfer that to the student. And there's plenty of ways to do so. But mainly we'll talk about this using the logits. For those that don't know, logits are the output of a model before it goes through a softmax. So think of this as image classification. Let's say you're trying to classify something as a bird, a cat, or a dog. When you throw this through a model, it'll just say, hey, I think it's a dog with a 1, I think it's a cat with a 0, and I think it's a bird with a 0. And that's what's the output of the model. However, before the softmax, you get what's called the logits, or the kind of like the confidence of the model. So for instance, it will say the dog at 0.9, the cat at 0.3, and the bird at 0.01. And after softmax, I guess turns into the binary values. But we can use the logits, or our soft labels, as a form of special knowledge, because maybe the teacher model has a hard time of identifying the difference between a dog and a cat because they might look similar. Interestingly enough, those logits alone actually say something about them all. They teach the child model that, hey, these inconsistencies or being unable to distinguish a dog from a cat says that might be something important for us to learn in our student model. And so while it might not be training with the hard ones and zeros, keeping these or trying to take the loss of these soft labels instead of the hard labels, which are the true outputs, can do a really good job of transferring that knowledge from the teacher model down to the student. So if you compared training via these soft labels compared to training from scratch via the true labels, you can actually see that the soft labels does a really good job of creating a similar network as the original pre-trained teacher. Oh yeah. Yes, exactly. Instead of trying to predict ones, zeros, and zeros, it's trying to get as close as possible to that teacher model. So doing so, hopefully we can transfer some of that knowledge or distill the knowledge into that smaller model that we've created. Yeah. So in actual knowledge distillation, you'll do a combination of both. You'll be training both using true labels and the soft labels from the teacher model. Does anyone else have any questions about knowledge distillation? I went through knowledge distillation and quantization pretty quickly, but we'll be mainly focusing on pruning for the coding bit. Yeah, there's a lot of different ways to transfer knowledge from the student model. Another thing you can do is transfer knowledge from the gradients. So when you do back propagation, you can try to make sure when you calculate the gradients, you want the gradients to be the same rather than just those output logits. Oh, I have the slide. This goes to show it a little bit better where we see here when we're trying to predict a dog, cat, or truck, the model identifies that as most likely a dog, but can maybe be a cat, and it's definitely not a truck. And because we know it's definitely not a truck, that might teach the student model or child model something a little bit about what weights it should be trying to aim. Forgot I had this one. And again, there's other methods that exist that look at intermediary layer knowledge. So, for instance, if you took two networks that had the same amount of layers, you could try to match up maybe the second layer of the student model to the second layer of the teacher model, try to have those weights be similar. A quick review of things. So if you were taking anything out of it, just kind of get the basic understandings of one, why do we want to have compressed models or smaller models outright? And then the three main methods. So pruning, which is removing or zeroing out the non-essential weights or components. Quantization, reducing the precision of the weights and therefore reducing the size of storage and how fast we can compute it. And knowledge distillation, using a teacher model to train a student model with intermediary layer information. Does everyone have any questions before we move over to the code?
It's just on quantization. It may seem kind of simple and not very big deal, but there's actually what I'm referring to specifically is that there was a LLM that quantized down to a single bit. So instead of a 32-bit float, the weights were just a bit that was a 1 or a 0, and obviously they had a lot more weights. The model ended up being a lot smaller, and it was still quite effective with single bit weights, which is interesting and kind of rewrites the whole idea of how neural network works when you take it down that small.
Mm-hmm. Yeah, absolutely. I forgot to mention I was going to have this be a bit of a challenge for you guys later on. But when we go to prune networks, oftentimes we can prune networks up to like 1% or even 0.001% of the original model size. A lot of these networks really don't need to be as big as they are now. And same thing with quantization. Sometimes, depending on the framework and the model exactly, you can reduce the size or the numerical data all the way to binary weights as well. I have no idea how that worked, but I remember reading up about it and being really interested. So yeah, let's go ahead and move on to our Colab. So we'll be doing this with the link here, tinyrl.com/nncompress. You need to be signed into your UCSC account. Once you're at the link, make sure to create a copy of the notebook, otherwise you won't be able to save your changes. And for this one in particular, you'll have to be using a GPU runtime. So I can go show how to do that in a bit, but make sure to select the T4 GPU as your runtime for these models.
Pick it up.